Now the second type of improper integrals that we'll consider are ones which have discontinuous integrands. And one way we can imagine this is to consider the case when we're integrating a function where, say, the interval over which we're integrating has a vertical asymptote either at one of the endpoints or somewhere in between one of the endpoints. So for instance, here in this picture we have a vertical asymptote in the graph at the right endpoint b. So what would be the way that we can integrate this function from a to b if it has a discontinuity here at the right endpoint b? So consider the case here where f is continuous on the interval from a to b where it's open at b, and it's discontinuous at that right endpoint at b. Then the integral from a to b is equal to the limit as t approaches b from the left of the integral from a to t. So notice this is kind of like the picture that we saw a moment ago, right, where we're integrating the function from a to b, but b is really a vertical asymptote in the graph. The graph looks something like that. So we take the integral from a to t of that finite region, and then we see what happens as t approaches b, in this case from the left side. Okay, similarly, if f is continuous on the interval from a to b where it's open at a, and we have a point of discontinuity at a, then the limit as the integral from a to b is equal to the limit as t approaches a from the right of the integral from t to b. And again, here we can imagine that perhaps we have a vertical asymptote at that left endpoint of the graph, or of the interval. And so, yeah, the graph maybe approaches infinity as it approaches that vertical asymptote. But here maybe we've got the integral from t to b, right, will be a value, an integral that we can evaluate, and then we just take the limit as t approaches a, in this case from the right. Okay, so here we have essentially an unbounded region in the sense that it's got a vertical asymptote in the graph. So it would be unbounded graphically when that graph approaches the vertical asymptote. So it's very possible that in these cases we get an infinite area, but we'll see that in some cases it actually is a finite value. And then the third possibility is that we have a vertical asymptote that occurs somewhere in between a and b. And so if that happens, right, if a function has a point of discontinuity at a point c, where c is in between a and b, then we can consider the two integrals from a to c and from c to b separately. And if each of these converge, then their sum will converge to the value of the integral from a to b. Okay. So let's try an example. Suppose I want to evaluate the integral from 2 to 5 of 1 over the square root of x minus 2. Notice that this has a discontinuity at x equals 2. So how can we evaluate it? Well, we're going to write this as the limit as t approaches 2 from the right, and then integrate from 2 to 5. Right? And we'll see now, when we evaluate this limit, do we get a finite value or do we get an infinite value? Now, to evaluate this limit, to evaluate this integral, I'll write x minus 2 to the negative 1/2 power. So integrating here, it's like doing the integral of u to the 1/2, right? Or u to the negative 1/2. which would just be 2u to the positive 1/2. So we'll have the same integral here with just x minus 2 instead of u. So it'll be 2 times x minus 2 to the positive 1/2 power. And then we'll evaluate from t to 5. Okay, so this will be, again I'm writing the limit every time. And then at the very end we'll evaluate the limit. But now let's see, we've got 2 times 5 minus 2 is 3 to the 1/2 power, minus 2 times t minus 2 to the 1/2 power. Okay. What I notice now is that as t approaches 2 from the right, this limit here will go to 0. And so there we have 2 times 3 to the 1/2 power minus 0, so it'll just be 2 times the square root of 3. Okay, so this one has a finite area. Let's consider the integral from 0 to pi over 2 of the graph of secant x. We want to determine, does this converge or diverge? We know that secant x, if we remember graphically, has a vertical asymptote at pi over 2. The graph of secant from 0 to pi over 2 looks something like this, where it flows up there as it goes to pi over 2. So we'll take the limit as t approaches pi over 2 from the left side now. Integral from 0 to t. And secant x dx. We know the integral of secant, remember, will be ln, absolute value of secant x plus tangent x. And then evaluate from 0 to t. So we'll evaluate it at t, so that'll be ln of secant t plus tangent t minus ln of secant of 0 is 1, tangent of 0 is 0, and then ln of 1 will be 0. So now we just have to evaluate the limit as t approaches pi over 2 from the left of secant t plus tangent t. Well, we know that as t approaches pi over 2 from the left, secant of t will actually go to infinity. So that part of it will blow up. But what about tangent t? What happens to tan t? Well, tan t also goes to infinity, right? Tangent also has a vertical asymptote at pi over 2 as well. So both of these will go to infinity, and therefore ln of something that approaches infinity must also approach infinity. So this limit is equal to infinity, so therefore the integral diverges. Now notice in this integral we have the integral from 0 to 3, and the function that we're integrating has a point of discontinuity at x equals 1. So what we need to do is consider, since x equals 1 is in between 0 and 3, we need to consider the integral from 0 to 1 and then the integral from 1 to 3 separately. And since each of these have the discontinuity at one of the endpoints now, we'll write each of them as limits. So this one will be the limit as t approaches 1 from the left side, integral from 0 to t. This one will be the limit as t approaches 1 from the right side, integral from t to 3. So this limit will be, or this integral will be ln of x minus 1, evaluated from 0 to t. This limit will be the same integral, ln of x minus 1, evaluated from t to 3. So let's see what we get. Here, ln of t minus 1 minus ln of the absolute value of 0 minus 1. Will just be absolute value negative 1, which is ln of 1, which of course is 0. And let's see, so this will be ln of 3 minus 1, so ln of 2 minus ln of t minus 1. Okay, so now evaluating each of these limits, I know that ln of t minus 1 will be approaching ln of 0. Keep in mind that ln of 0 is undefined, and we know that actually as the graph approaches 0 of ln x, it'll go to negative infinity, right? So ln of x goes to negative infinity as x approaches 0 from the right. So in both this case and this case, it'll go to negative infinity. So since just that piece alone is going to diverge, we can say that overall the whole thing will diverge. So here we'll say divergent. Now in this example, we're looking at the integral of ln of x on the interval from 0 to 1. And again, we can kind of imagine the picture we saw a moment ago, where we have the graph of ln x. We know we'll approach negative infinity here as it approaches 0. So we have that discontinuity at x equals 0. So we'll take the limit as x approaches 0 from the right. Here I'm going to use the letter t instead of x actually. And then integrate from t to 1. To remind you, we did the integral of ln of x in the section on integration by parts. So to remind you how we did that, you let u equal to ln x, dv is equal to dx. So du is 1 over x dx, and v is equal to x. So when we do parts, get u times v is x ln x minus the integral of v times du. It's the integral of x times 1 over x. So we get x ln x minus the integral of just 1 times dx. So it's x ln x minus x. So just a little reminder of how that integral works. So let's put the answer in here. So we got the limit as t approaches infinity, or sorry, t approaches 0 from the right. Integral of ln x, what we showed here was x ln x minus x. And then we'll evaluate from t to 1. So this will be 1 times ln of 1, which is 0, minus 1, minus, then evaluating it at t will be t ln of t minus t. Okay. And it looks like here we get an indeterminate form because we've got, okay, so we can take the limit as t approaches 0 from the right. For this term will just be negative 1, of course. And then, of course, for this term, it'll be 0. So we'll just focus on taking the limit as t approaches 0 from the right of t ln of t. Notice this is an indeterminate form since ln of t goes to negative infinity and then t goes to 0, so it's 0 times infinity. So to write it in a form where we can evaluate it using L'Hopital's rule, I'm going to write ln of t over the reciprocal of t. So now you see it's in the infinity over infinity form. So now I'll just do a little L'Hopital's rule. Derivative of ln of t in the numerator will be 1 over t. Derivative of 1 over t in the denominator, remember that's t to the negative 1, so the derivative will be negative t to the negative 2. And then simplifying that, we get negative t squared over t, so that'll be just negative t. And then as t goes to 0 from the right, we just get a negative t evaluated at 0, which is 0. So our answer will just be negative 1. So now we've shown that the area of this region here between 0 and 1 on the ln x graph is equal to 1. Or sorry, is equal to negative 1. So the area is negative here, of course, because it's below the x-axis. But the actual area would be a positive value.